Hey everyone, and welcome to This Explainer. Today, we're going to decode the absolutely fascinating physics of 1D kinematics. We're going to look at exactly how everyday motion translates into some seriously elegant mathematics. Whether you're racing down a ski hill or just sprinting to catch a school bus, motion is a huge part of your everyday life. But how do we actually measure and describe it? Well, that is exactly what we're here to uncover.
Take a look at this. A long jumper doesn't just sprint and chuck themselves into the air hoping for the best, right? No way. They rely entirely on maximizing horizontal distance by mastering their speed, strength, and technique. In other words, they are directly applying the physical laws of kinematics to nail that winning jump.
But hold on a second. Before we can calculate the winning distance of a jump like that, we gotta step back and ask a deceptively simple question. What exactly is motion? I mean, we see it all around us constantly, but defining it scientifically, that requires us to be incredibly precise.
To figure that out, here's our roadmap. We'll start by defining motion and kinematics, move into categorizing scalars and vectors, understand position and displacement, calculate some total displacements, and finally, draw out vector scale diagrams. Let's jump right in. All right, Section 1, defining motion and kinematics.
So this first concept is absolutely crucial. It's the foundation for everything we're doing today. What is kinematics? Well, it's really just the term physicists and engineers use for the study of how things change location. Fundamentally, motion itself is just a change in the location of an object, as measured by an observer. Imagine you're standing at your front door, and you watch a friend running down the street to catch that school bus. From your perspective, as the observer, your friend is in motion, because their location relative to you is changing.
Moving right along to Section 2, scalars, vectors, and distance.
Okay, so in physics, we need a way to distinguish between different types of measurements, right? And we do this using two main categories that completely change the game for understanding movement. First up, the scalar. The big takeaway here is that a scalar quantity only cares about magnitude, and magnitude is really just a fancy, scientific word for size. Think about pure distance, which is the perfect example of a scalar. If you track your total distance walking 500 meters from your home to your school, your pedometer doesn't care if you walked north, south, east, or west. It only cares about the total magnitude of your trip, 500 meters. But think about it. What if you want to give a friend directions to meet you at that school? If you just say, hey, walk 500 meters, that doesn't really help. They could end up half a kilometer in the completely wrong direction. You need a vector. A vector adds a specific direction to that magnitude, like saying, walk 500 meters east. And notice that whenever we write a vector symbol in physics, we place a little arrow directly above it. That's just to remind ourselves that yes, direction absolutely matters here.
This example hits the nail on the head when comparing the two concepts. Imagine this exhausting path. You walk from your home to school, then to the library, and then you drag yourself all the way back home. Your total distance, that scalar path, might be a whopping 1,900 meters of walking. You're exhausted. But your displacement, which is the vector measuring the exact change in your position from your start line to your finish line, it's zero. Literally 0 meters, because you ended up exactly where you started. Displacement only cares about where you start and where you finish.
Which brings us nicely to Section 3, position and displacement. It all starts with position. Your position is basically your starting line, and we map it as a vector. It denotes your distance and direction from a specific reference point, usually the 0-meter mark. For example, if your home is your 0-meter reference point, we can say the school's position is exactly 500 meters east of your home. And notice that position gets that special D symbol with the vector arrow on top because, again, direction is key.
So, how does this build into displacement? Well, we calculate it by taking your final position and subtracting your initial position. You see that little triangle symbol? That's the Greek letter delta. In physics, whenever you see delta, just think change in. So delta D with the little arrow on top, that literally translates to change in position.
All right, let's put this into practice. Section 4, calculating total displacement.
Now that we've got the math formulas locked down, let's calculate some real-world total displacements. We can use this really handy 4-step problem-solving framework. Picture a dog in an agility competition. She darts 80 meters due west to fetch a ball, and then trots 27 meters due east to drop it in a bucket. How do we find her total displacement? Well, step 3, our analysis, says we use vector addition, but we've got a little problem. One vector is west and the other is east.
Here's where it gets super interesting. We use a neat little math trick. We can't just cleanly add east and west together. But What if we consider east to be the exact same thing as a negative west? Actually, yeah, that works perfectly. We just flip that 27 meters east so it becomes negative 27 meters west. Suddenly, our directions match up, making the algebraic addition a total breeze. Let's crunch the numbers. Adding her first displacement of 80 meters west to her second displacement of negative 27 meters west gives us 53. Boom! This means the dog's total final displacement is precisely 53 meters west of her trainer. She ran 107 total meters of distance, sure, but her actual displacement from her starting point is just 53 meters west.
Okay, home stretch. Section 5. Drawing vector scale diagrams. Let's put the algebra away for just a second. Vector scale diagrams are such a game changer because they let us visually map things out on a scaled grid, kind of like saying 1 centimeter on your paper equals 100 meters in real life. You represent each vector as a directed line segment. The end with the arrowhead is the tip, and the starting point is the tail. To add movements together, you literally just connect the tip of your first vector straight to the tail of your next one. Your total displacement is just a single straight line from your very first tail all the way to your final tip.
Let's make this concrete with an example. Imagine walking 200 meters north to a store. On your paper, you draw an arrow pointing north. Next, you walk 600 meters south to a friend's house. So, you draw a second, longer arrow pointing south, and you attach its tail right to the tip of that first arrow. Connecting those lines tip to tail visually proves exactly what the math tells us. Your total displacement from your house to your friends is a vector pointing exactly 400 meters south.
Let's wrap up our deep dive into motion with this handy little cheat sheet. It perfectly summarizes the big three. Distance is your scalar, measuring the total path. Position is a vector mapping a specific spot. And displacement is the vector measuring your total change in position. Going forward, whenever you're tackling kinematics problems, always check your symbols. Remind yourself, am I dealing with a magnitude-only scalar or a magnitude and direction vector? Now, I want to leave you with a challenge. Grab a piece of paper and try mapping out this practice journey yourself using that tip-to-tail method we just went over. If you walk 10 paces forward, 3 paces forward, and finally 8 paces backwards, what is your total displacement? See if you can calculate your exact change in position before your next physics class. Thanks for hanging out with me for this explainer, and definitely keep looking for the physics hidden in your everyday life.